Hello friends, let's move towards the fourth module of unit 5th, that is passband digital transmission. Today we are going to discuss DPSK, that is differential phase shift key. But before that, let's have a quick revision that what we have studied in last lecture. If you remember, in last lecture we have studied multi-level modulation technique, that is QPSK, quadrature phase shift keying. In quadrature phase shift keying, we came to know that there were four symbols over there: 0, 0, 0, 1, 1, 0, 1, 1. And according to this transition from symbol to symbol, there was a variation in the phase of the carrier signal. Then we have seen the generation of your QPSK, that is offset QPSK and non-offset QPSK. The difference between offset and non-offset QPSK is that a presence of a delay element. A delay element, when it is a present, it is called offset QPSK, due to which the even bit streams and odd bit streams, they are not going to occur simultaneously. They are not going to make a transition at the same instant of time. Whereas in non-offset QPSK, which is simply called as QPSK also, even bit streams and odd bit streams, the phase transition, it can occur at the same instant of time. They can go at the zero voltage at the same instant. So due to which there is an abrupt amplitude variations in your QPSK, that is non-offset QPSK, which is more pronounced as compared to your offset QPSK. After that, we have seen detection of your QPSK. Then we have seen the advantages, disadvantages of QPSK, and finally we have compared QPSK with your BPSK. So let's move towards our topics. As I told, today we are going to discuss DPSK, its generation and detection techniques, its advantages, disadvantages, and then comparison with coherent BPSK. Now, as we can see, differential phase shift keying as the non-coherent version of the PSK. In previous lecture, we have seen the coherent detection of your BPSK. Today we are going to see non-coherent version of your BPSK, which is also called as DPSK, that is differential phase shift keying. So it is a differentially coherent modulation method. DPSK, it doesn't need a coherent carrier at the demodulator. The input sequence of binary bits is modified such that the next bit, it depends on the previous bits. Therefore, in the receiver, the previous received bits are used to detect the present bit. Now, in order to eliminate the need for this phase synchronization of coherent receiver with your PSK, we are going to use a differential encoding system. So, the digital information content of this binary data is encoded in terms of signal transition. I repeat, please pay attention that digital information content of the binary data is encoded in terms of signal transition, because over here what phase is going to change. As an example, symbol 0, it may be used to represent your transition in a given binary sequence with respect to previous encoded bits. So symbol 0, it is going to represent what? Transition. Otherwise, symbol 1, it is going to indicate no transition. So the new signaling technique which combines this differential encoding with phase shift keying is also known as what? Differential phase shift keying. So hope so you understood why we are calling it as differential phase shift keying, because we are going to use a differential encoding. Differential encoding in the sense what? The binary sequence, it is going to depend on the previous bit of your encoded bit. It means the transition. So it is combined with your phase PSK. That's why it is called what? DPSK. This is the block diagram of your DPSK. As this figure you can see on the screen, that first it is consist of your encoder. Encoder, it has two inputs, B of k and D of k minus 1. Now the output of this encoder, it is called a D of k, that is encoded output. If this encoded output is delayed by a period of TB, then its output is given by D of k minus 1 because it is delayed by 1 unit TB. So the delayed version of this encoded output and this input binary data, these are the what input of this encoder, and output of this encoder along with this time delay, it is as a one of the input of this product modulator. And this product modulator, it has a carrier sinusoidal wave which has fixed amplitude A and which has a fixed frequency, that is f of c. So the output of this product modulator is nothing but your multiplier of this your encode data and your carrier wave. So it would be plus minus AC cos 2 pi FCT. Now DPSK, basically it is the method of BPSK where there is no reference phase signal it is used because it is non-coherent detection. Here the signal which is transmitted is used as what? Reference signal. So this modulation, it encodes two separate signals, that is carrier signal and the modulating signal, and the phase shift of each signal, it is of 180 degree. Now in the previous figure we have seen that serial input data, it is applied to the encoder, and mainly that encoder, it consists of what? XNOR gate, and the output of that logic gate is fed back again to the input via 1-bit delay circuit as we have seen. So both the carrier signals as well as the XNOR gate output is applied to what? Balance modulator, so that the modulated signal of DPSK signal, it could be generated. Now let's understand this concept. So we are assuming that this is a binary data, that is B of k, which is nothing but a one of the input to the encoder. So we are taking input as your 0 0 1 0 0 1 0 0 1 1. Now as I already told, this is for your reference, that symbol 0, it is going to indicate what? It is going to indicate the transition in the given binary sequence with respect to its previous encoded bit. So if there were a transition between the input binary sequence and its encoded previous encoded bit, then we are going to denote this encoded bit as symbol 0. If there is no transition it is there, then such symbol, it is denoted by symbol 1. Now this is your differentially encoded data. So in order to start this sequence, basically we have to assume over here it could be logic 1 and it could be logic 0. This star mark, it is going to indicate this. It is what? For the reference purpose we have taken this logic 1 over here. You can also take logic 0. In next table we can see of logic 0. So at the initial stage we have assumed that output of this encoder at the initial start, it is what? Logic 1. So as you know, since the binary input it is of 0 and its previous encoded data it is what? 1. So since there is a transition, and as we know, if there is a transition, then it is represented by symbol 0. So see, symbol 0, it is going to tell you what? Transition. Similarly, this is your next binary sequence and its previous input encoded data is 0. So is there any transition? No. 0 0, so there is no transition, and as we know, since there is a no transition, it is going to represent what symbol? 1. Similarly, the next binary input is 1. So if it is going to compare this binary 1 with its previous encoded bit, it is what? No transition, it is there. 1 1 it is there. So what would be the output? Output, it is symbol 1. Symbol 1, what it represents? It represents no transition. Similarly, next binary sequence, it is what? 0, and its previous encoded bit is 1. So it means there is a transition. So if there is transition, then we are going to represent this transition as symbol 0. Similarly, next is what? No transition. So it is represented by symbol 1. Again, no transition, 1 1. So it is going to be represented by symbol 1. Next, there is a transition, that is 1 0. So if there is transition, it is represented by symbol 0. After that, again you can see the next input binary compared with its previous encoded bit, it is what? No transition, 0 0. So output, it would be what? Symbol 1. Similarly, no transition, 1 1. So output is symbol 1. No transition between 1 1. So again it is represented by symbol 1. So hope so you understood this one. Now, next is your phase of your DPSK signal. As you know, that symbol 0, it is going to represent what? Transition. So if there is a transition, the phase of that DPSK signal, it would be represented by what? Pi, because the maximum phase change in DPSK is represented by pi. So next, you can see that next binary input, a differential encoded data, it is what? 1. Since 1, it represents no transition, so phase of this DPSK signal, it is represented by 0. Again, next differentially encoded data, it is a symbol 1. Symbol 1, it represents what? No transition. Since no transition, no phase change. Similarly, it is symbol 0. It means transition. So there is this phase change. You can see 1, no transition. So no phase change, no transition, no phase change. Since symbol 0, which represents transition, so phase change, it is of pi. Next is again 1 1 1. So it means no transition. So the phase change occurred at your of d key of d of k, it would be what? Represented by 0. Now, the delayed version of this received DPSK signal, it has been shown in the 4th row of the table. So you can see this one. This is d of k, and as I told that encoder, it has a 2 inputs, that is bk, and second one, it is what? Delayed version of this encoded data. So what is the 1 bit delayed data? It is what? D of k minus 1. So you can see that we have shifted, we have delayed by 1 bit, that is 1, it would be come over here, 0 1, this one, it would come over here, 0 would come over here, and so on. So hope so up till now you understood this, your that how this shifted version of encoded data it came. Now, the phase angle of this DPSK and its delayed version, it has been shown in 3rd and 5th rows respectively. So you can see that one. This is a phase of your DPSK signal, that is D of k, and this is a phase of shifted DPSK. So this 0, it came over here, this pi, it came over here. Similarly, this 0, it has come over here, this pi, it came over here, 0, this 0, pi, 0, and this 0, and this 0 we have taken over here. So what is this row? 5th row, it is going to tell you the shifted version of this phase of this DPSK. Now, the phase difference between the two sequences for each bit interval is used to determine the sign of the phase comparator output. When phi equal to 0, the integrator output is positive, whereas if it is pi, then integrator output is negative. And by comparing the binary sequence by assigning a symbol 0 for negative output and symbol 1 for positive output. Now we would see that. Now what we have to do it, we have to compare it. What we have to compare it? We have to compare the phase of DPSK and the phase of shifted DPSK. So you can see from this one that there is a change of the phase, that is a pi to 0. So it is comparison, we have compared it. This is a transition, there is a transition. So it is going to be represented by minus sign. And similarly, this phase, it is what? 0 pi, again it is 1 minus, sorry. And since this phase and this phase, it is 0 0, so no change over here, so we are going to represent it by positive sign. Next, pi to 0, there is a change, so represented by minus sign. 0 to pi, again there is a change, represented by minus sign. 0 0, no transition, so represented by plus sign. Pi to 0 minus, 0 to pi minus, 0 0, no transition in the phase, so represented by plus sign. And at the last, again 0 0, no transition, it is represented by plus sign. Now the reconstructed binary data, it is shown in the last row of this table. So you can see that since the phase comparison output, it is going to tell you, it is going to decide the detected binary sequence, that is the recovered signal, right? So what is this? Since minus, it is represented by 0, as I already told, minus 0. Since it is a plus, represented by symbol 1. Minus 0 0 1, this is 0 minus 0, this is plus, represented by 1 1. So if you can observe this one, this binary data and its detected binary version sequence, it is one and same. So hope so you understood this table. Now moving towards the detection of your DPSK. So this is the block diagram of your detection of DPSK. It consists of your band pass filter, then it is a multiplier. This multiplier, it is consists of this DPSK signal, and this is a delayed version of this DPSK signal by 1, and it is given to product modulator. Then it has been given to this integrator, that is a low pass filter, and the unit multiplier, which encases multiplier, and this integrator, it is called as what? Correlator. And output of this correlator, it is given to your decision device, which is compared with threshold of 0 volt. So if it is greater than this one, y is greater than 0, then it is taken as symbol 1, and if it is less than 0, it is taken as 0. So in this demodulator, the received DPSK signal is applied to one of the input of multiplier, and to the other input of the multiplier, a delayed version of the received DPSK signal by the time delay TB, it is applied, as we just seen. So the output of this multiplier is ready to release in the direction of low frequency using low pass filter, that is your integrator. And after that, it is transmitted towards a shaper circuit for improving the unique binary data like the output. Here the shaper, it could be your comparator or it could be your Smith trigger circuit. Now we are going to see the next table, but over here what I told, the binary data, it is same as we have seen in the previous data, 0 0 1 0 0 1 0 0 1 1. But what is the difference over here? The difference is that this differentially encoded data, that is a reference data, we have taken it as a 0. In the previous table, we have taken what? 1. But since at the initial state it could be 1 or 0, so we have taken the example with the help of 1. Now we are going to take this example. If the initial state, the output of the encoder is 0, then what would be the result? Now we are going to see it. As I told that since differentially encoded data, it is what? 0, and the binary input, it is 0. Since there is a no transition, this 0 and 0, no transition. So as we know the no transition, it is represented by what? Symbol 1. Next, since the next binary sequence, it is 0, and when we are going to compare it with its previous encoded bit, it is 1. So there is a transition, 1, 0. So what would be the output? Output would be the symbol 0, and symbol 0, it is going to represent what? Transition. Similarly, next binary sequence, it is what? 1, and its previous encoded bit, it is what? 0. So what would be the output? The output would be what? 0. Similarly, no transition, what would be the output? Symbol 1. There is a transition, so output would be indicated by symbol 0. There is a transition, so output would be symbol 0. No transition indicated by symbol 1. Similarly, there is a transition, so represented by symbol 0. Again transition, symbol 0. Last, there is a transition, so it is represented by symbol 0. So hope so you understood this. Now moving next point. Phase of this DPSK signal. What I told that symbol 0, it is going to represent what? Transition. So if there is a transition, it means there should be the phase change. So this symbol 0, it is represented as what? Pi, that is a transition, and 1, it is going to represent what? No transition, no phase change. So that's why we have written over here 0, 0, 0 and 0, and rest symbol zeros are there, so it is going to indicate what? Transition, which is indicated by pi. So this delayed version of this received DPSK signal, it is shown in the 4th row of the table. So you can see that one. So you can see this one, that shifted differentially encoded data, that is d of k minus 1, 1 by unit of 1. So this 0, it came over here, 1, this one, 0, 0, it came, 1 came over here. So all these encoded data, it is shifted by 1, and it is shown in this 4th row of this table. Now moving next, the phase angle of the DPSK signal and its delayed version, it has been shown in row 3rd and 5th, and the difference between this 3rd and 5th row, that is it is called a phase angle. So now you can see this is a phase of shifted DPSK. See, this pi came over here, 0 came over here, this pi came over here, this is 0, pi, and so on. As like your encoded data is shifted, similarly the phase of the DPSK signal, it is also shifted. Now the phase difference between the two sequences for each bit interval is used to determine the sign of the phase comparator output, and if this phi is 0, the integrator output is positive, whereas if it is pi, its output is negative. And by comparing the binary sequence by assigning the symbol 0 for negative output and symbol 1 for positive output. Let's see this one. Now compare the phase of the DPSK and its shifted version of DPSK. There is a transition, and this transition is represented by what? Minus sign. Similarly, pi to 0, there is a transition, so it is represented by minus sign. Pi to pi, no transition, it is there, so represented by plus. 0 to pi, minus, since transition. Pi to 0, again transition, indicated by minus sign. Pi to pi, no transition, so indicated by plus sign. 0 to pi, minus, pi to 0, minus sign, and last pi to pi, plus, and pi to pi, this is indicated by plus sign. Now we are going to see the reconstructed binary data, which is shown in this last table. So you can see that comparator output minus sign is represented by 0 and plus sign is represented by 1. So minus 0, minus represented by 0, plus represented by 1, and so on. Now compare this detected binary sequence and the transmitted binary data. You will observe that it is one and same. So what is the conclusion now? what conclusion you can make it now from this two table. So the conclusion is that the reconstruction of the DPSK signal is invariant with the choice of the initial bit in the encoded data. Either you can take 0 or 1. We have proved, we have seen in both the table, irrespective of the choice of this extra bit, that is the initial bit, the reconstructed bit, it is invariant. It is not going to vary. So this is the most important conclusion of your DPSK. Moving towards the end of this lecture, advantages of DPSK. Thus, modulation doesn't need the carrier signals at the end of the receiver circuit. Therefore, compound circuits are not required. The bandwidth of DPSK requirement is low as compared to your BPSK modulation, and the non-consistent receivers are simple, inexpensive to construct, and therefore extensively used in wireless communication. But the drawbacks, the disadvantages, the bit error rate or the chance of error is high in DPSK as contrast to BPSK. Also, the interference of noises in DPSK is more. This modulation, it employs what? Two consecutive bits, which is intended for its response. Thus, error in the primary bit makes an error with a subsequent bit, as well as consecutively it is going to spread the error. Also, in DPSK, as we know that previous bit it is used to detect the next bit. Hence, if error it is present in the previous bit, then the detection of this next bit it also be wrong. So hence, error is created in next and it is carry forward, and there is a tendency of appearing errors in your pairs in DPSK. Now, what are the applications of your DPSK? The applications of DPSK mainly include as wireless communication like your RFID, wireless LAN and Bluetooth. Now last, we are going to now compare the performance of your DPSK with BPSK. So you can see what is the variable characters. The variable characteristic in BPSK and DPSK it is same, that is phase. Second, the bandwidth is also same, that is FB. Probability it is low, probability of error it is low in BPSK, but in DPSK it is higher than your BPSK, as I already explained in drawbacks of it. Next, noise effect. Noise effect it is low in your BPSK, where it is higher than BPSK in DPSK. Similarly, requirement of your synchronous carrier, it is required in BPSK, whereas it is not required in your DPSK, because DPSK it is what? Non-coherent version of your this coherent BPSK. So that's why we don't require the synchronous between the transmitter and receiver carrier. Last, 6, it is your system complexity. The complexity of the system is definitely lower than your DPSK for binary phase shifting, whereas it is complexity a little bit hard for this, higher than your BPSK. Then last, it is a demodulation technique. It is both synchronous for BPSK and DPSK. So now, moving towards the summary of this lecture. Today we have studied that DPSK it is nothing but a non-coherent version of your BPSK. Then we have studied that differentially encoded technique it has been used along with your phase shift keying. That's why we call it as what? Differential phase shift keying. And from that table, we have taken the initial bit 0 also and 1 also, and in both the table we came to know at the last the reconstructed data it is same as that of what? Your transmitted data. So it means the reconstruction of your DPSK signal it is invariant. It doesn't depend on the choice of this starting bit. You can take it 0 or 1, but at the last you would get the original or reconstructed data which you have transmitted. Then we have seen that what are the advantages of your DPSK, what are its disadvantages. Then we have seen the comparison of your DPSK with BPSK, how they perform, and it's all about our today's lecture. This is the assignment, so please note down this assignment. In next module, we are going to study M-array PSK. It is also a multi-level modulation technique. Its geometrical representation, the power spectral density, and advantages and disadvantages of it. This is my email ID shown on the screen. So it's about all today's lecture. Thank you very much.